Welcome to Ultimate Sleep Doctor. Subscribe for new soothing facts weekly. Tonight we'll explore 100 calm facts about volcanoes. Close your eyes, get lost in the depths, and drift to sleep. Let's begin. The Earth's interior, a realm of immense heat and pressure, holds a story of constant creation and dramatic release. It's a story that plays out not with earthquakes and shifting landscapes, though those are certainly linked, but with the very substance of our planet, molten rock. The formation of volcanoes isn't a sudden, explosive event. It's a protracted process, beginning far, far beneath the surface. The heat that fuels this process isn't simply residual warmth from the Earth's formation. It's generated by radioactive decay within the Earth's core and mantle. Uranium, thorium, and potassium isotopes constantly breaking down, releasing energy in the form of heat. This heat, combined with the immense gravitational pressure, forces lighter materials within the mantle, primarily peridot, a magnesium iron silicate, to rise. As these materials ascend, they experience a decrease in pressure, and this reduction in pressure causes them to partially melt. It's not a complete liquefaction. Rather, a partial melt occurs, creating what we call magma. This initial magma is often quite viscous, meaning it's thick and resistant to flow. It's driven upwards by the buoyant force of its lower density compared to the surrounding solid rock. This upward movement isn't a straight, forceful surge. It's a slow, painstaking process, like pushing a large, heavy object through a dense medium. The magma's journey is impeded by the surrounding solid rock, forcing it to circulate and accumulate in areas of weakness or fractures within the crust. Over millions of years, this accumulation builds up, creating what are known as magma bodies. As this magma accumulates, the processes continue. More heat from the mantle radiates upwards, and more radioactive decay occurs, further fueling the melting of surrounding rock. The magma becomes increasingly abundant, and the pressure within the magma chamber grows. This increasing pressure forces the magma to flow more readily, creating channels and pathways within the surrounding crust. The characteristics of the magma, its composition, viscosity, and gas content, are critical to understanding the nature of the potential eruption. Different magma compositions, for instance, those rich in silica, tend to be more viscous, meaning they hold gases more effectively. This can lead to more explosive eruptions, while magmas with lower silica content tend to be less viscous and produce gentler flows. The rate of magma generation is also influenced by factors like temperature and stress within the crust. Faulting and fracturing provide conduits for magma to ascend, and the movement of tectonic plates plays a fundamental role in creating and modifying these pathways. Over immense timescales, these accumulating magma bodies grow into substantial reservoirs, what we call magma chambers. These chambers can range in size from a few kilometers across to hundreds of kilometers, and they are typically located at considerable depths within the Earth's crust, often several kilometers below the surface. These chambers aren't static. They are constantly evolving, changing in size and composition due to the ongoing influx of new magma and the removal of material through eruptions. The pressure within these chambers is immense, far greater than the pressure exerted at the surface. This pressure exerts a powerful force on the surrounding rock, causing it to bulge outwards, creating the characteristic volcanic cone shape. The geometry of these chambers, their shape and size, profoundly affects the style and intensity of an eruption. Now, let's consider the broader context of volcanic activity: plate tectonics. The Earth's lithosphere, the rigid outer layer consisting of the crust and the uppermost part of the mantle, is broken up into several large plates that are constantly moving, albeit very slowly, typically a few centimeters per year. This movement is driven by convection currents within the mantle, where hotter, less dense material rises and cooler, denser material sinks. This movement is the primary cause of most volcanic activity on our planet. There are three main types of plate boundaries where volcanism is most common. The first is at divergent plate boundaries, where plates are moving apart. At these boundaries, magma rises to fill the gap created by the separation, often forming mid-ocean ridges, underwater mountain ranges where new crust is continuously created. The second type occurs at convergent plate boundaries, where plates collide. Here, one plate can subduct, plunge beneath another. As the subducting plate descends into the mantle, it heats up and releases water, which lowers the melting point of the surrounding mantle, generating magma. This magma then rises to the surface, creating volcanic arcs, chains of volcanoes, often found parallel to the subduction zone. The Andes Mountains in South America and the Cascade Range in North America are prime examples of volcanic arcs. The third type of plate boundary involves transform faults, where plates slide horizontally past each other. While not as directly associated with explosive volcanism, movement along these faults can create zones of weakness in the crust, leading to localized volcanic activity. The Ring of Fire, encircling the Pacific Ocean, is a particularly concentrated area of volcanic and seismic activity, directly linked to the movement of the Pacific Plate and its interactions with surrounding plates. It represents the largest zone of ongoing plate tectonic activity on Earth. The formation of volcanoes isn't simply a consequence of molten rock. It's inextricably linked to the dynamic processes occurring within our planet's interior. The Earth's mantle is a system of incredible complexity, constantly churning and reshaping itself, and volcanoes are one of the most visible manifestations of this ongoing transformation. The study of volcanoes allows us to understand these deep processes, providing invaluable insights into the fundamental workings of our planet. As we consider the sheer timescale involved, millions of years, it's clear that volcanic activity represents a fundamental element of Earth's long-term evolution, a powerful reminder of the forces constantly at play beneath our feet. Volcanoes, these powerful expressions of our planet's inner workings, are often depicted as forces of destruction, but they represent a fundamentally creative process. They are the visible consequence of immense geological forces, sculpted over vast stretches of time. Understanding their formation illuminates the dynamic nature of the Earth itself. Let's delve into the diverse mechanisms that birth these magnificent landforms, beginning with their presence at divergent plate boundaries. At divergent plate boundaries, the Earth's crust is being pulled apart. This isn't a violent ripping, but rather a slow, relentless stretching. Consider the island nation of Iceland, situated directly atop the mid-Atlantic ridge. This ridge is a colossal underwater mountain range, a prime example of a divergent boundary. As the North American and Eurasian tectonic plates move apart, often by just a few centimeters each year, magma rises to fill the void. This magma, less dense than the surrounding rock, ascends through the fractures and weaknesses created by the spreading plates. It doesn't erupt with explosive force in the same way as volcanoes formed in other settings. Instead, it tends to produce relatively gentle, effusive eruptions, flowing lava that forms extensive shield volcanoes. These volcanoes grow outwards, building themselves over time through the accumulation of basaltic lava flows. The magma composition here is typically rich in magnesium and iron, contributing to the characteristic dark color of the lava. The process is incredibly gradual, but over millions of years, it has built up the dramatic landscape of Iceland, a testament to the power of plate tectonics at its most serene. The very ground beneath your feet is being reshaped by this slow, deliberate separation. Now, let's shift our focus to a dramatically different, and arguably more intense way volcanoes are created: convergent plate boundaries. Here, instead of plates moving apart, they collide. This collision generates tremendous pressure and heat, initiating a process known as subduction. Subduction occurs when one tectonic plate slides beneath another. This isn't a smooth, graceful descent, it's a complex interaction involving immense friction and deformation. The plate that's forced beneath, the subducting plate, is typically a denser oceanic plate, sinking into the Earth's mantle. As it descends, it encounters increasing temperatures and pressure, causing it to partially melt. This partial melting is critically important. The water trapped within the minerals of the subducting plate is released into the hot, rising magma. This water plays a revolutionary role in altering the properties of the magma. Without this addition of water, the magma would remain incredibly viscous, thick, and resistant to flow. However, the presence of water dramatically reduces the viscosity, making the magma significantly more fluid. The effect is comparable to adding a surfactant to a paint, reducing its thickness and allowing it to spread more easily. This fluid magma, now capable of flowing more readily, ascends towards the surface. The depth at which this melting occurs can vary, but often it's at depths of tens of kilometers. The resulting magma, infused with water, is capable of producing the most spectacular and dangerous volcanic eruptions. The subduction zone itself becomes a zone of intense volcanic activity. As the water, rich magma rises, it encounters the overlying continental crust or another oceanic crust. This interaction often leads to the formation of a volcanic archy, a chain of volcanoes that runs parallel to the trench where the subduction occurs. The Andes Mountains in South America, for instance, are a classic example. The subduction of the Nazca Plate beneath the South American plate has created a chain of volcanoes stretching thousands of kilometers. These volcanoes are not simply the result of magma rising from depth. They are profoundly shaped by the process of subduction and the associated influx of water. Consider the Mariana Trench, the deepest part of the world's oceans. It's formed by the subduction of the Pacific Plate beneath the Philippine Sea Plate. The intense pressure and temperature, coupled with the release of water from the subducting plate, create conditions perfectly suited for magma generation. The volcanoes associated with this subduction zone, including the islands of Guam and the volcanoes on the slopes of the Mariana Islands, are frequently associated with explosive eruptions. The viscosity of the magma is reduced by the water, allowing it to ascend quickly and build up tremendous pressure. When this pressure is released, it results in powerful, cataclysmic eruptions. The role of water isn't simply a minor addition to the magma, it's a fundamental catalyst. Without it, the Earth's volcanoes would be fundamentally different. The viscosity of the magma would be so high that it wouldn't be able to rise effectively, and the eruptions would be far less frequent and less energetic. The movement and interaction of water within the Earth's mantle is a cornerstone of our planet's geological activity. It's a constant, albeit slow, process reshaping our world. The heat from the Earth's core, combined with the presence of water, drives a continuous cycle of melting and renewal, creating new landforms and influencing climate patterns across the globe. As we consider the immense scale of geological time, it's clear that volcanoes aren't just isolated events. They are integral components of a continuous, dynamic system. They represent the tangible expression of the forces shaping our planet, a visible reminder of the ongoing processes occurring deep within. The formation of volcanoes is a testament to the Earth's incredible power and resilience, a force that has shaped continents, sculpted landscapes, and ultimately influenced the very existence of life as we know it. These silent giants, constantly building and reshaping the world, provide an unparalleled opportunity to study the processes that govern our planet's evolution. Volcanoes, in their raw and elemental form, represent one of the most powerful forces shaping our planet. They are geological expressions of immense heat and pressure, constantly reminding us of the dynamic nature of the earth beneath our feet. To truly understand a volcano's behavior, we need to delve into the very substance from which it erupts: magma. The composition of this molten rock is the key to unlocking the secrets of its behavior, determining whether it will calmly flow across the landscape or unleash a spectacular, explosive display. As we consider the diversity of volcanic eruptions, it's crucial to recognize that not all magma is created equal. The primary factor influencing a volcano's style is the silica content, a measure of the chemical complexity of the molten rock. Silica, essentially a compound of silicon and oxygen, plays a pivotal role in determining the viscosity of the magma, that is, its thickness or resistance to flow. Magmas rich in silica, like rhyolite and dacite, are incredibly viscous. This high viscosity means the magma struggles to flow easily, becoming almost like a very thick, sticky honey. When a magma with high silica content encounters existing rock formations, it tends to be trapped, building up pressure until it finally erupts with tremendous force. Conversely, magmas low in silica, like basalt, are much more fluid. They flow more readily, allowing for gentler, more expansive eruptions. Let's examine basaltic magma, a frequent contributor to some of the most impressive and, importantly, relatively predictable volcanic events. Basalt is the most common type of magma found on Earth, representing approximately 60–70% of all volcanic eruptions. It's characterized by a low silica content, typically around 45–55%. This low silica level translates directly into a low viscosity, a fluidity that allows basaltic magma to flow with considerable ease. Eruptions resulting from basaltic magma are almost always effusive, meaning they involve the outpouring of lava. We see this in classic shield volcanoes, such as those found in Hawaii and Iceland. The lava flows are often broad, gently sloping, and incredibly long, sometimes stretching for hundreds of kilometers. The low viscosity allows the lava to travel great distances before cooling and solidifying. These flows aren't typically violent, though they certainly pose a significant hazard due to their immense heat and volume. The eruptions are characterized by the steady, continuous release of lava, often accompanied by the formation of lava tubes channels, formed by the flowing molten rock, which then solidify, leaving behind hollow pathways. The geological record shows numerous examples of basaltic eruptions creating vast, smooth plains composed entirely of solidified basaltic lava. However, the Earth's volcanic systems are far more complex than simply categorized as high silica or low silica. Moving into the middle ground, we encounter magmas with intermediate silica content, offering a fascinating spectrum of eruption styles. Andesite magma, for example, falls into this category, possessing a silica content typically ranging from 55–65%. This intermediate composition results in a viscosity that is higher than basalt but lower than rhyolite. As a consequence, andesitic magmas typically produce eruptions that are explosive yet somewhat predictable. The increased viscosity compared to basalt creates a greater resistance to flow, leading to the buildup of pressure as gases within the magma try to escape. The shape of the surrounding rock formations plays a crucial role here. If the surrounding rock is relatively weak and easily disrupted, the pressure buildup can lead to a more explosive eruption. However, even with an intermediate viscosity, andesitic magma can still flow, and the eruptions often manifest as lava domes, bulbous masses of solidified lava that grow within the vent of the volcano. These domes are frequently associated with phreatic eruptions, where magma interacts with groundwater, generating steam and further escalating the explosive potential. The formation of lava flows is also common, though they tend to be more viscous and channeled than those produced by basaltic magma. The volcanoes that produce andesite magma, such as Mount St. Helens in the United States, provide excellent examples of these complex, intermediate eruption styles, showcasing the dynamism of volcanic systems. The viscosity of magma isn't the only factor influencing eruption style. The gas content within the magma is equally important. Magmas typically contain dissolved gases, primarily water vapor, carbon dioxide, and sulfur dioxide. As magma rises towards the Earth's surface, the pressure decreases, allowing these gases to expand. This expansion generates tremendous pressure, further contributing to the explosive force of an eruption. The ratio of gas content to magma viscosity is what ultimately determines whether an eruption will be gentle or violent. A magma with a high gas content and a low viscosity is far more likely to produce a highly explosive eruption, while a magma with a low gas content and a high viscosity will tend to produce a more effusive, less violent event. The geological record documents numerous examples of volcanoes exhibiting these varied behaviors, shaped by the interplay of magma composition and gas content. The study of volcanoes is an ongoing process, a constant investigation into the forces shaping our planet. By meticulously analyzing magma composition, gas content, and the surrounding geological environment, scientists are able to develop increasingly sophisticated models to predict volcanic behavior. These predictions are vital for mitigating the risks associated with these powerful natural phenomena, safeguarding communities and enabling a deeper understanding of the Earth's dynamic processes. The ongoing monitoring of active volcanoes, utilizing techniques such as seismology, gas monitoring, and ground deformation measurements, provides invaluable data to refine our knowledge and enhance our ability to anticipate and respond to volcanic hazards. Ultimately, our understanding of volcanoes is inextricably linked to our appreciation of the Earth's immense power and the profound influence it exerts on shaping our world. Let's delve into the fascinating and sometimes terrifying world of volcanoes. These geological forces, born from the heart of our planet, represent a constant reminder of the immense power simmering beneath the surface. It's a world of intense heat, dramatic transformations, and landscapes sculpted by molten rock. We'll be focusing today on some key aspects, beginning with the nature of the magma itself. Much of what happens at a volcano is dictated by the composition of the magma. Different magmas possess markedly different characteristics, and understanding these variations is crucial to comprehending the type of eruption we're observing. One particularly important type is rhyolitic magma. Rhyolite is a silica-rich magma, meaning it contains a high proportion of silicon dioxide. This high silica content is what gives it its distinctive properties. It's incredibly viscous. Viscosity refers to a material's resistance to flow. Rhyolitic magma is significantly more viscous than, for example, basaltic magma, which is much lower in silica content. This high viscosity means the magma doesn't flow easily. It's like honey compared to water. The thick, slow-moving nature of this magma contributes directly to the most explosive eruptions we see from volcanoes. The trapped gases within the magma, pressurized by the heat, can't escape as readily. When the magma is forced upwards, the increasing pressure builds until it overcomes the strength of the surrounding rock, resulting in a violent release of energy, a catastrophic eruption. These rhyolitic eruptions are often characterized by the ejection of pyroclastic flows, which are superheated currents of gas and volcanic debris traveling at incredible speeds, and the formation of ash clouds that can spread for hundreds, even thousands, of kilometers. Now, let's turn our attention to the forms that lava takes as it flows across the landscape. The appearance of lava flows varies dramatically, and these variations provide us with valuable clues about the magma's viscosity and cooling rate. Two primary textures are commonly observed: pahoaho and ea. Pahoaho, derived from the Hawaiian words poho, meaning ropey or smooth, describes a lava flow with a smooth, rope-like appearance. This texture develops when the lava surface is cool enough to form a skin. As the lava continues to flow beneath this skin, it creates undulating, wave-like patterns. The surface remains relatively smooth due to the formation of this skin. The cooling process is crucial here. A slower cooling rate allows for the formation of this characteristic texture. Ea, on the other hand, describes a much rougher, blockier lava flow texture. A comes from the Hawaiian word for scorched or parched. This texture develops when the lava flows rapidly over a cooler surface. The rapid flow causes the lava to fragment into angular, jagged blocks, creating a surface that resembles a shattered volcanic rock. Essentially, the rapid cooling and fragmentation occur before a smooth surface can form. The difference between pahoeho and is often a direct consequence of the lava's viscosity and the rate at which it cools. It's important to understand the distinct terminology associated with volcanoes, particularly when discussing their overall structure. We often hear the terms crater and caldera used, and while they're both depressions at the summit of a volcano, they represent fundamentally different geological features. A crater is typically formed by the direct act of an eruption. It's a bowl-shaped depression created by the explosive ejection of material, often during a Plinian eruption, during the eruption itself. It's a relatively small feature, formed relatively quickly in comparison to a caldera. Think of it as the immediate impact zone of a powerful eruption. A caldera, however, is a much larger and more complex geological feature. A caldera is formed by the collapse of the ground above a partially emptied magma chamber. After a prolonged period of volcanic activity, the magma chamber beneath a volcano can become increasingly depleted. As the magma supply diminishes, the roof of the chamber loses support, causing it to collapse inward, creating a large, cauldron-like depression. These calderas can be tens of kilometers across and often contain smaller volcanic cones formed by subsequent eruptions. The Yellowstone caldera in the United States is a prime example. It's a vast, roughly circular depression approximately 60 by 80 kilometers in size, formed by several cataclysmic eruptions over millions of years. The formation of a caldera is a process that unfolds over much longer timescales than the formation of a crater. It's a testament to the immense forces at play within the Earth's crust and highlights the dynamic nature of volcanic systems. Examining the scale of these features offers a profound sense of geological time. It allows us to appreciate how slowly, over millennia, the landscape around a volcano can be reshaped. The study of calderas helps scientists understand the long-term behavior of volcanic systems and the potential for future eruptions. Considering the interplay between magma composition, lava flow textures, and the formation of craters and calderas provides a comprehensive framework for understanding volcanic activity. Each of these processes is intricately linked, and changes in one can profoundly impact the others. The continuous cycle of magma generation, eruption, and landscape modification is a constant reminder of the powerful forces shaping our planet. Volcanic systems represent a continuous feedback loop of geological activity, a dynamic system responding to changes deep within the Earth's mantle. Understanding this system is critical not only for appreciating the beauty and drama of volcanoes, but also for assessing and mitigating the hazards they pose. The ongoing monitoring and research surrounding volcanoes are vital for protecting communities living in volcanic regions, and for furthering our knowledge of these incredible geological phenomena. The Earth's crust is a living, breathing entity, constantly evolving through the processes we observe at volcanoes, a powerful demonstration of the planet's enduring energy. Let's turn our attention now to the diverse forms that volcanoes can take, understanding the geological processes that shape these incredible displays of Earth's power. It's a landscape sculpted by intense heat and unimaginable pressure, a realm of constant creation and, occasionally, devastating release. We'll explore some of the most prominent types, beginning with those that appear remarkably serene in their form, yet possess a tremendous internal energy. Consider the shield volcanoes. These formations, found predominantly in volcanic regions like Hawaii and Iceland, represent a fundamentally different approach to lava creation compared to the more explosive volcanoes we might initially picture. The key lies in the viscosity of the lava itself. Shield volcanoes are built from relatively fluid basaltic lava flows. Basalt is a volcanic rock characterized by its low silica content, which dramatically reduces its viscosity, how easily it flows. This low viscosity lava, under the immense pressure deep within the earth, spreads out over considerable distances, forming broad, gently sloping flanks. The resulting shape resembles a warrior's shield lying on the ground, hence the name. These flows are not like the thick, viscous streams that cause such violent eruptions. Instead, they move outwards in relatively thin sheets, accumulating over millennia. The Hawaiian Islands, for example, are a testament to this process. Chains of shield volcanoes, each a product of repeated basaltic eruptions. The sheer volume of lava produced over countless years has built these massive landforms, a slow, deliberate process of construction guided by the consistent flow of molten rock. As we consider the scale of these formations, it's important to appreciate the immense timescale involved. The formation of a single shield volcano can take hundreds of thousands, even millions, of years. It's a testament to the patient, persistent force of volcanic activity. Now, let's shift our focus to a very different kind of volcano, the stratovolcano. These are often referred to as composite volcanoes, and they represent a more complex and dynamic scenario. Stratovolcanoes are characterized by their steep, conical shapes, far more dramatic than the gentle slopes of shield volcanoes. Their formation is rooted in alternating layers of lava flows and pyroclastic material, ash, cinders, and volcanic bombs. This layering is the key to their distinctive appearance and their greater potential for explosive eruptions. The lava, in this case, is typically andesitic or rhyolitic, which are significantly higher in silica content than basalt. This increased silica content dramatically increases the viscosity of the lava, making it much thicker and stickier. When this highly viscous lava encounters existing magma chambers or attempts to push upwards, it becomes trapped, leading to pressure buildup. This pressure, combined with the presence of volatile gases like water vapor and carbon dioxide, can trigger powerful, explosive eruptions. The pyroclastic material, ejected during these eruptions, adds to the steep slopes of the volcano. Each layer of ash and rock contributes to the gradual accumulation of material, building the conical shape we recognize. Mount Fuji in Japan, for instance, is a classic example of a stratovolcano. The alternating layers of lava flows and pyroclastic deposits have created a strikingly steep-sided mountain, a potent symbol of Japan's volcanic activity. The dynamic nature of stratovolcanoes, the interplay between flowing lava and explosive eruptions, makes them significantly more dangerous than shield volcanoes. Let's delve now into a fascinating geological feature, often found at the summit of volcanoes, the volcanic neck. These are remnants of solidified lava pillars, a direct consequence of volcanic activity. As a volcano erupts, the magma chamber beneath it begins to empty. As the eruptions cease, the remaining magma can still be mobile, albeit at a slower rate. During periods of relative quiescence, lava may continue to flow upwards, attempting to reach the surface. However, the surrounding pressure often prevents this, causing the lava to solidify within the vent. Over time, the softer, surrounding volcanic material is eroded away, leaving behind the hardened pillars of solidified lava. These pillars, often strikingly geometric in shape, are called volcanic necks or lava domes. depending on their structure. They represent the final, solidified expression of the magma's passage. The shape of a volcanic neck is intimately linked to the cooling rate of the lava. Rapid cooling leads to the formation of smaller, more angular necks, while slower cooling results in larger, smoother domes. These necks stand as silent witnesses to past eruptions, offering a tangible connection to the powerful forces that shaped the surrounding landscape. They are often significantly eroded compared to the surrounding volcanic edifice, emphasizing the transient nature of volcanic activity. Consider the geological timescale once again. The formation of a volcanic neck can take thousands, even tens of thousands, of years, a process intimately linked to the gradual cooling and erosion of solidified lava. It's a reminder that volcanic landscapes are constantly evolving, with older features being shaped and reshaped by the relentless forces of nature. The study of volcanic necks provides valuable insights into the subsurface magma plumbing systems of volcanoes, allowing geologists to reconstruct past eruptive events and assess the potential for future activity. Finally, let's contemplate the sheer diversity within the volcanic world. Shield volcanoes, stratovolcanoes, and volcanic necks represent just a small selection of the many forms that volcanoes can take. Each type is shaped by unique geological processes, influenced by the composition of the magma, the tectonic setting, and the prevailing environmental conditions. The study of volcanoes is not merely about understanding catastrophic events. It's about comprehending the fundamental processes that drive the creation and evolution of our planet. It's about recognizing the power and the beauty inherent in geological forces, and appreciating the extraordinary forces that continue to shape our world, one molten flow, one explosive eruption, one solidified pillar at a time. Let's delve into the captivating and often destructive power of volcanoes. These geological formations, born from immense heat and pressure within the Earth, represent a fundamental aspect of our planet's dynamic processes. Understanding their creation and behavior is key to appreciating their significance and to recognizing the potential impacts they can have on the surrounding landscape and, indeed, on human populations. The origins of a volcano are rooted in the theory of plate tectonics, a concept that describes the Earth's outer shell, the lithosphere, as being broken up into several large plates that are constantly moving, albeit incredibly slowly, relative to one another. These movements create stress, and where these plates collide, slide past each other, or diverge, immense amounts of heat are generated from the Earth's interior. This heat fuels the formation of magma, molten rock, which is less dense than the surrounding solid rock, causing it to rise towards the surface. Consider, for instance, the formation of a lava dome. This is a strikingly beautiful, yet inherently unstable, geological feature. A lava dome isn't formed through a simple, flowing extrusion of magma. Instead, it represents a prolonged accumulation of viscous, often silica-rich, lava. As magma pushes upwards through the crust, it may encounter resistance. This resistance causes the magma to partially solidify, creating a bulbous, rounded mass. Over millions of years, repeated intrusions of magma, punctuated by periods of solidification, build up this dome-shaped structure. The lava within the dome is typically very thick and sticky, resisting flow, and this is why the resulting formations tend to be rounded and relatively undisturbed by the surrounding landscape. The layering within a lava dome, representing different stages of cooling and solidification, can be incredibly visible, offering a tangible record of the volcanic process. These domes often occur at the summit of a volcano or in large flanks and are a testament to the protracted, slow-moving nature of magma accumulation. They demonstrate how the seemingly gentle, persistent flow of magma can, over immense timescales, sculpt some of the most dramatic geological features on our planet. However, The formation of lava domes is just one part of the story. Equally significant are the more violent and rapid processes associated with volcanic eruptions. A particularly dangerous phenomenon is the pyroclastic flow. These aren't your typical lava flows. They're far more intense and destructive. A pyroclastic flow is a searing current of hot gas and volcanic debris. It's generated when a column of hot gas and volcanic ash, often associated with an explosive eruption, is pushed rapidly upwards. This column can then collapse, creating a turbulent, ground-hugging flow that races down the flanks of a volcano at speeds exceeding 100 kilometers per hour. The temperature within these flows can reach hundreds of degrees Celsius, and the force with which they impact the surrounding terrain is enormous. The combination of heat and pressure is devastating, capable of incinerating everything in its path: vegetation, rock, and structures. The composition of a pyroclastic flow varies, depending on the eruption style and the materials present, but it generally consists of ash, pumice, volcanic rock fragments, and superheated gas. Understanding the characteristics of pyroclastic flows is crucial for hazard assessment and mitigation efforts in areas prone to volcanic activity. Now, let's consider the contrasting style of eruption known as an effusive eruption. These are characterized by a constant outpouring of lava. They are typically associated with basaltic magmas, which are relatively fluid and low in silica content. This fluidity allows the magma to flow more easily over considerable distances. We often see this in shield volcanoes, which are named after their broad, gently sloping shape. The lava, as it flows, can travel for kilometers, sometimes even tens of kilometers, before cooling and solidifying. The color of the lava can vary greatly depending on its composition and the gases it contains. Pahoeho lava, characterized by its smooth, rope-like appearance, is formed when gas bubbles are squeezed out as the lava cools. Conversely, a blocky, or opie, lava surface is formed when the lava cools rapidly, creating a fractured surface. The heat radiating from these flows can create a surreal landscape with steam vents and pools of molten rock. The viscosity of the lava plays a critical role in determining the flow patterns, with lower viscosity leading to faster, more extensive flows. These flows can dramatically reshape the surrounding landscape, creating new channels, lava plains, and altering the topography in a remarkably short period of time. The continuous, albeit often dangerous, outpouring of lava is a fundamental aspect of the volcanic cycle. The effects of volcanic activity extend far beyond the immediate area of an eruption. The ash produced by explosive eruptions, or even the flows from effusive eruptions, can travel enormous distances, blanketing vast regions in a layer of volcanic debris. This ashfall can disrupt transportation, damage infrastructure, contaminate water supplies, and cause respiratory problems. Furthermore, the release of volcanic gases, such as sulfur dioxide, carbon dioxide, and hydrogen sulfide, can have significant environmental impacts, contributing to acid rain, affecting air quality, and potentially harming vegetation and animal life. The long-term effects of volcanic activity also include changes in climate, as volcanic gases released into the atmosphere can influence cloud formation and reflect sunlight back into space, potentially leading to temporary cooling periods. The study of volcanoes, known as volcanology, is a complex and multidisciplinary field encompassing geology, chemistry, physics, and atmospheric science. Scientists use a variety of techniques to monitor volcanoes, including seismographs to detect earthquakes, gas sensors to measure volcanic emissions, GPS to track ground deformation, and satellite imagery to monitor changes in the volcanic landscape. This continuous monitoring is crucial for detecting signs of unrest and providing early warnings of potential eruptions, allowing for timely evacuation and mitigation efforts. The Earth's volcanoes continue to be an active area of scientific research. offering valuable insights into our planet's dynamic processes and posing ongoing challenges for communities living in volcanic regions. The sheer power contained within these geological formations is a humbling reminder of the forces that have shaped and continue to shape our world. Volcanoes, in their rawest form, represent a fundamental display of the Earth's internal energy, a constant, powerful reminder of the forces that shape our planet. They are geological spectacles, often terrifying in their intensity, but also incredibly complex and, when understood, surprisingly beautiful in their workings. The study of volcanoes is intertwined with an understanding of plate tectonics, magma generation, and atmospheric chemistry, offering a window into the very processes that formed and continue to mold the landscapes we see around us. Let's delve deeper into the kinds of eruptions we observe, exploring the distinct characteristics that define these dramatic events. Consider, for instance, the nature of strombolian eruptions. These are some of the most commonly observed volcanic activity globally, and they are frequently characterized by intermittent, explosive bursts of gas and lava. The term strombolian comes from Stromboli, a small island in the Tyrrhenian Sea, where this type of eruption is most prominently displayed. These aren't massive caldera-forming events. Instead, they're a series of relatively small, repeated explosions, often lasting for hours or days. The process begins with gas, primarily water vapor, carbon dioxide, and sulfur dioxide, building up pressure within the magma chamber beneath the volcano. This magma, typically basaltic in composition, meaning it's relatively low in silica content, is already partially molten. As the pressure increases, the gases find pathways to the surface. These eruptions aren't continuous. They're punctuated by periods of relative quiet, during which the volcano settles into a state of activity. The explosions themselves aren't driven by a huge, instantaneous release of energy. Rather, they're the result of the gas bubbles within the magma expanding rapidly as they rise towards the surface. These expanding bubbles create shock waves, culminating in the bursts of material, typically incandescent lava, ash, and rock fragments that we witness. The eruptions themselves can be quite unpredictable, with the frequency and intensity varying over time. Some strombolian volcanoes display a very regular pattern of activity, while others are more erratic. The shape of the volcanic cone itself often reflects the nature of these eruptions, with steep, sided slopes formed by the accumulation of pyroclastic material, the fragmented rock ejected during the explosions. These cones, like strombolis, are a testament to the power of these repeated, yet controlled, releases of energy. Now, let's shift our focus to a significantly different type of volcanic eruption, phreatic eruptions. These events are frequently associated with greater danger and can be far more unpredictable than strombolian activity. Phreatic eruptions arise from the interaction between magma and water, most commonly groundwater, but also surface waters such as lakes or oceans. The key here is the rapid heating of water by the superheated magma. Magma, especially when it's in contact with water, can reach temperatures of several hundred degrees Celsius. When this extremely hot magma comes into contact with water, the water instantly vaporizes, creating a massive, superheated steam explosion. Unlike strombolian eruptions, which are driven by gas pressure, phreatic eruptions are fundamentally steam explosions. The steam expands explosively, shattering rock and propelling fragments of rock and magma into the air. These explosions can be incredibly violent, and they often create characteristic features such as phreatomagmatic craters, bowl-shaped depressions formed by the violent mixing of magma and water. The intensity of a phreatic eruption depends largely on the amount of water present and the temperature of the magma. A small pocket of water interacting with moderately hot magma might produce a relatively mild explosion, whereas a significant body of water encountering extremely hot magma can generate an incredibly powerful eruption. One of the most dramatic examples of a phreatic eruption occurred at Mount Unzen in Japan. The interaction of magma and seawater created a massive steam explosion that collapsed the summit crater, triggering a series of subsequent, even more violent eruptions. As we consider these differing eruption styles, it's important to note that many volcanoes exhibit a combination of characteristics. It's not always a clear-cut distinction between strombolian and phreatic activity. Often, a volcano will display intermittent bursts of gas and lava, interspersed with periods of steam explosions. The magma itself plays a crucial role in determining the type of eruption. Basaltic magma, as we've discussed, is generally associated with more frequent, smaller eruptions like strombolian activity. It has a lower viscosity, meaning it flows more easily, allowing the gases to escape more readily. In contrast, more viscous magmas, those rich in silica, tend to trap gases, leading to higher pressures and the potential for more explosive eruptions. These high silica magmas, such as rhyolite or dacite, are commonly found at subduction zones, where tectonic plates are forced beneath one another and can generate extremely powerful, cataclysmic eruptions, often associated with the formation of large calderas. Calderas are immense, bowl-shaped depressions formed when a volcano collapses after a massive eruption has emptied the magma chamber beneath. The collapse creates a void that can then fill with water, further enhancing the potential for phreatic activity. The scale of volcanic activity is also influenced by factors beyond the magma itself. The geometry of the surrounding landscape, the availability of groundwater, and the proximity to bodies of water all play a significant role. Volcanoes located near coastlines or in areas with abundant groundwater are naturally more susceptible to phreatic eruptions. Furthermore, the rate at which magma ascends through the crust is a critical factor. Rapid ascent can lead to more explosive eruptions as the gases are forced upwards more quickly. Conversely, a slow, steady ascent allows for more gradual degassing, reducing the risk of explosive events. Understanding these diverse eruption styles is not simply an academic exercise. It's fundamentally important for hazard assessment and mitigation. By recognizing the characteristics of different volcanic systems, scientists can develop more accurate models of volcanic behavior and provide timely warnings to communities living near active volcanoes. Monitoring techniques, such as seismic monitoring, gas emission measurements, and ground deformation tracking, are essential tools in this endeavor. The ongoing study of volcanoes provides invaluable insights into the processes that shape our planet, reminding us of the immense power residing within the Earth's interior and the dynamic nature of the geological world around us. The interplay of magma, water, and the surrounding environment continues to produce some of the most dramatic and awe-inspiring events on Earth. Volcanoes hold a profound power, a force sculpted over oons, shaping landscapes and impacting climates across the globe. Their activity is rarely predictable, and understanding the processes behind their behavior is key to appreciating both their beauty and their potential danger. We'll delve into some of the most fascinating aspects of volcanic systems, beginning with the truly dramatic phenomenon of phreatomagmatic eruptions. These aren't simply eruptions of molten rock. They represent a far more complex and violent interaction, a meeting of fire and water that unleashes extraordinary energy quietly beneath the surface. Magma chambers exist, vast reservoirs of molten rock heated by the Earth's internal heat. This magma isn't always a smooth, flowing substance. Sometimes, it encounters subterranean water sources, groundwater, aquifers, or even the water accumulated from past eruptions. When magma interacts with water, the results are transformative. The water instantly vaporizes, undergoing a rapid phase change. This vaporization dramatically increases in volume, expanding with incredible force. The magma itself is already under immense pressure, and this sudden expansion creates a shock wave that propagates through the surrounding rock. It's a chain reaction. The initial shockwave fractures the rock, creating voids and pathways. The superheated magma then rushes into these fractures, further accelerating the expansion and generating even more intense pressure. This creates a chaotic, fragmented eruption, a phreatomagmatic eruption, combining the explosive power of a volcanic eruption with the extreme energy of a steam explosion. The pressure generated is far greater than that produced by a typical magma eruption, and the resulting blasts can reach phenomenal distances, sometimes traveling hundreds of kilometers. The ash produced in these events is often composed of fine particles, carried aloft by the powerful winds, and can blanket vast areas, posing significant hazards. Consider the impact of these events on the surrounding landscape. The energy released is sufficient to excavate deep craters, sometimes hundreds of meters in diameter. The fragmentation of the rock itself is far more pronounced than in a typical lava flow eruption. The material ejected, known as tephra, is incredibly diverse in size and composition, depending on the specific conditions of the eruption. We can now examine the different types of tephra and their characteristics. Ash, the smallest component, consists of fine particles of pulverized rock and glass, typically less than 2 millimeters in diameter. These particles are incredibly lightweight and can be carried by the wind for hundreds, even thousands of kilometers, impacting air travel and posing respiratory hazards. Pumice is a volcanic rock that has been so extensively fractured by gas bubbles during its formation that it is almost entirely porous. It's lightweight, incredibly fragile, and can float on water. While it might appear harmless, pumice clasts, even relatively large ones, can cause significant damage due to their abrasive nature. Volcanic bombs are perhaps the most visually striking form of tephra. These are large, rounded fragments of solidified lava that have been ejected during an eruption. They can range in size from a few centimeters to over a meter in diameter, and their size is directly related to the velocity at which they were propelled from the vent. The formation of these bombs involves lava fragments being carried upwards within the rising magma column, solidifying as they are exposed to the cooler temperatures, and then being violently ejected during the eruption. The impact force of a volcanic bomb is substantial, and they can cause localized devastation, particularly when they land on structures or people. The distribution of tephra isn't uniform. The shape and intensity of the eruption determine the pattern of deposition. High-intensity phreatomagmatic eruptions create broad, diffuse deposits, while lower-intensity events may produce more concentrated layers. The thickness and composition of these deposits are vital indicators for scientists studying past eruptions and predicting future hazards. These deposits, often referred to as tephra layers, provide a geological record, allowing us to reconstruct the sequence of past eruptions, understand the evolution of volcanic systems, and ultimately assess the potential for future events. The study of these layers is a cornerstone of volcanology. We use techniques such as radiocarbon dating and magnetostratigraphy to accurately determine their age and composition. The study of tephra also informs hazard assessments, allowing us to identify areas that are most vulnerable to future eruptions. Beyond the immediate effects of phreatomagmatic eruptions, the longer-term consequences are equally significant. The massive amounts of ash released into the atmosphere can have a profound impact on global climate. Fine ash particles can block sunlight, leading to a temporary cooling effect. This volcanic winter can disrupt agriculture, affect ecosystems, and contribute to widespread societal disruption. The deposition of ash can also alter drainage patterns, influencing river flows and contributing to soil fertility. As we consider the vast timescales involved in volcanic activity, it's clear that these processes are intimately linked to the geological evolution of our planet. Volcanoes aren't just destructive forces. They are also agents of creation, transporting molten rock and ash, shaping landscapes, and contributing to the formation of new landmasses. The Pacific Ring of Fire, encircling the Pacific Ocean, is a particularly active zone of volcanic activity, driven by plate tectonics, the movement of Earth's lithospheric plates. These plates constantly interact, causing subduction, where one plate slides beneath another, generating immense heat and pressure that fuels magma formation. The study of volcanic processes is a complex and multidisciplinary endeavor, drawing upon geology, chemistry, physics, and even climate science. Each eruption is unique, influenced by a multitude of factors, including the magma's composition, the amount of water present, and the surrounding geological setting. Ongoing monitoring of volcanoes through seismographs, gas sensors, and deformation measurements is crucial for detecting changes in activity and issuing timely warnings to communities at risk. The goal is not to simply predict eruptions, but to understand the underlying processes and build a robust system of hazard assessment and mitigation. The legacy of volcanic activity extends far beyond the immediate event. Volcanic soils, formed from the weathered volcanic rock, are remarkably fertile, supporting diverse ecosystems and contributing to agricultural productivity. Furthermore, the economic benefits derived from geothermal energy, harnessing the heat from volcanic sources, demonstrate our ability to coexist with these powerful forces. Studying volcanoes teaches us about the dynamic nature of our planet, the forces that have shaped its surface, and the importance of preparedness and resilience in the face of natural hazards. The sheer scale and power of volcanic activity serves as a humbling reminder of our place within the Earth's grand, ongoing story. Let's delve into a truly awe-inspiring and, at times, terrifying aspect of our planet's geological forces, volcanoes. They represent a raw, elemental power, a reminder of the dynamic processes shaping the very surface of Earth. Understanding volcanoes isn't simply about knowing about eruptions. It's about grasping the immense forces that operate beneath our feet, forces that have molded continents and continue to sculpt our world. We'll consider the diverse ways these geological marvels influence the environment and, critically, the potential dangers they present. The most immediately recognizable impact of volcanic activity is, of course, ashfall. The fine, gritty particles ejected during an eruption, often composed of pulverized rock and glass, can travel incredible distances, carried aloft by the prevailing winds. A moderate ashfall can disrupt air travel, forcing the closure of airports across vast regions. Planes are incredibly sensitive to even small amounts of volcanic ash in the engine intakes, and the damage caused by a single particle can lead to catastrophic engine failure. Beyond aviation, ashfall poses significant challenges to human health. Inhaling volcanic ash can cause respiratory problems, irritation of the eyes and skin, and exacerbate existing conditions like asthma. The sheer volume of ash settling on buildings, roads, and agricultural lands creates immediate logistical difficulties, requiring extensive cleanup efforts and impacting infrastructure. The composition of the ash itself is a crucial factor. Ash containing sulfur compounds, for instance, can react with moisture in the air to form sulfuric acid, a corrosive substance that further complicates cleanup and poses a risk to water sources. The extent of the ashfall is directly related to the size and intensity of the eruption, but wind patterns and atmospheric conditions play a significant role in determining its dispersal. Some eruptions produce explosive ash clouds that can reach hundreds, even thousands of kilometers, while others generate more localized fallout. As we consider the devastating potential of ashfall, it's vital to understand another incredibly dangerous hazard, associated with volcanoes' pyroclastic density currents. These are arguably the most lethal aspect of volcanic activity, representing a truly terrifying force. Unlike the relatively gentle flow of lava, pyroclastic currents are incredibly fast, moving flows of hot gas and volcanic debris. They form when a column of hot gas and ash is disrupted, often by an explosion or the collapse of a volcanic slope. This disruption creates a pressure wave that races down the volcano's flanks at speeds exceeding 100 kilometers per hour, sometimes even surpassing the speed of a jet aircraft. The density of these currents varies. Some are relatively dilute, consisting primarily of hot gas, while others are incredibly dense, resembling turbulent flows of concrete. Regardless of their density, the temperatures within these currents can reach hundreds of degrees Celsius, enough to instantly incinerate anything in their path. They travel down valleys, across slopes, and even across water, carrying with them a lethal combination of heat, high-speed movement, and abrasive volcanic debris. The destructive power of a pyroclastic current is staggering, capable of obliterating entire settlements in a matter of minutes. Unlike lava flows, which tend to follow predictable pathways, pyroclastic currents can move in unpredictable directions, making escape incredibly difficult. They represent a sudden, overwhelming threat, demanding respect and immediate awareness during volcanic events. The formation and behavior of these currents are influenced by several factors, including the geometry of the volcano's slopes, the nature of the eruption, and the surrounding topography. Volcanic activity isn't solely defined by ashfall and pyroclastic flows. The molten rock, or lava, itself presents a considerable hazard. Lava flows, although typically moving at a slower pace than pyroclastic currents, can still cover vast areas, destroying anything in their path. The viscosity of the lava and its resistance to flow is a key factor determining its behavior. Highly viscous lava, which is thick and sticky, tends to flow slowly, creating broad, relatively gentle flows. Conversely, more fluid lava flows can travel much faster, particularly when they encounter pathways with slopes. The color of the lava also provides clues about its composition and temperature. Dark, colored lava is generally cooler and more viscous, while lighter, colored lava is hotter and more fluid. The interaction between lava flows and the environment can have profound long-term effects. For instance, extensive lava flows can create new landforms, gradually reshaping landscapes over thousands of years. They can also alter soil chemistry, impacting plant growth and the overall ecological balance. Beyond the immediate, visible effects, volcanoes also play a crucial role in the global climate system. Large eruptions can inject enormous quantities of sulfur dioxide gas into the stratosphere, where it can form sulfate aerosols. These aerosols reflect sunlight back into space, leading to a temporary cooling effect on the Earth's surface. The magnitude of this cooling effect depends on the size of the eruption and the persistence of the aerosols in the atmosphere. Historically, massive volcanic eruptions have coincided with periods of significant climate change, although the precise relationship is complex and debated among scientists. The deposition of volcanic ash and aerosols can also affect cloud formation, further influencing climate patterns. The geological processes surrounding volcanoes, the formation of magma, the movement of tectonic plates, and the interaction between magma and groundwater are intimately linked. Many volcanoes are located along plate boundaries, where tectonic forces are concentrated. The movement of these plates generates immense heat and pressure, ultimately leading to the melting of rock and the formation of magma. The creation of volcanoes is therefore a direct consequence of the planet's dynamic interior. Studying volcanoes isn't just about understanding immediate hazards. It's about gaining insights into the fundamental processes shaping our planet. By monitoring volcanic activity through techniques like seismic monitoring, gas analysis, and ground deformation measurements, scientists can develop increasingly accurate predictions of eruptions. This knowledge is crucial for protecting communities living near volcanoes and mitigating the potential impacts of these natural disasters. The ongoing research into volcanic processes continues to refine our understanding of the Earth's interior and the forces that drive geological change. The study of volcanoes reminds us of the powerful, often unpredictable, forces at work beneath our feet, emphasizing the importance of respecting the natural world and appreciating the intricate connections that shape our planet. Let's delve into a subject of immense power and raw, elemental force: volcanoes. These geological giants have shaped continents, altered landscapes, and, throughout history, presented a stark reminder of the Earth's dynamic nature. They are born from processes deep within our planet, a testament to the heat that continues to build and reshape the world around us. The scale of volcanic activity is almost impossible to truly grasp, a constant, underlying current of energy that occasionally erupts in spectacular and, undeniably, destructive displays. The very nature of a volcano reveals a fundamental truth about our planet, that it is not a static entity, but one in a perpetual state of transformation. Quietly beneath our feet, molten rock, known as magma, resides within the Earth's mantle. This magma isn't simply a solid substance, it's a complex mixture of molten rock, dissolved gases, and mineral compounds. The heat driving this process is primarily residual heat from the planet's formation, combined with the heat generated by radioactive decay within the Earth's core. The pressure exerted by the overlying rock mass prevents this magma from rising to the surface, but given enough time and sufficient weakness in the crust, it will find a pathway to escape. The most visible manifestation of this escape is, of course, the lava flow. These flows are a consequence of the magma's ascent, and their destructive potential is immense. Lava flows can travel at astonishing speeds, reaching temperatures of over 1,000 degrees Celsius. They consist of molten rock, gases, and ash, and their impact on the surrounding environment is profound. They can incinerate everything in their path, transforming forests into desolate landscapes and reshaping entire valleys. The sheer volume of lava flowing from a volcano can displace vast quantities of material, altering drainage patterns, destroying infrastructure, and forcing the evacuation of communities. Historically, many settlements have been obliterated by lava flows, a tragic reminder of the raw power of these geological events. The distance a lava flow can travel depends on several factors, including the viscosity of the lava, the slope of the terrain, and the availability of channels for its movement. Some flows can move for kilometers, while others are contained within a more limited area. Scientists carefully monitor volcanic activity, using techniques like seismology and gas monitoring to predict the likelihood of eruptions and to assess the potential hazard posed by lava flows. However, the dangers posed by volcanoes extend beyond the immediate impact of flowing lava. Equally devastating, and often more unpredictable, are lahars. These are volcanic mudflows, a truly terrifying combination of volcanic debris and water. The formation of a lahar begins with rainfall or melting snow and ice, often triggered by an eruption. This water rapidly mobilizes loose volcanic material, ash, pumice, and rock fragments, creating a dense, turbulent mixture. The consistency of a lahar can vary dramatically, ranging from a slurry resembling quicksand to a fast, moving torrent. Their destructive power is amplified by their speed and volume. Lahars can travel at incredible velocities, far exceeding the speeds of conventional floods. They are capable of tearing apart bridges, eroding riverbanks, and burying entire villages. The steep slopes surrounding volcanoes frequently channel lahars, accelerating their movement and increasing their destructive potential. The distances they can travel are typically longer than those covered by lava flows, often extending for dozens of kilometers. Scientists study the characteristics of lahars, their flow rates, sediment composition, and travel distances to develop hazard maps and evacuation plans for communities living near volcanoes. The ash produced by volcanic eruptions also presents a significant threat. Volcanic ash isn't just a nuisance. It's a finely ground abrasive material that can cause widespread damage. It can blanket entire areas, collapsing roofs, disrupting transportation networks, and contaminating water supplies. The ash's ability to clog machinery, obscure visibility, and disrupt communication systems can have far-reaching consequences. Moreover, the chemical composition of volcanic ash can pose health hazards, causing respiratory problems and skin irritation. Following an eruption, ashfall monitoring is crucial for assessing the extent of the hazard and issuing warnings to affected populations. The study of volcanoes is inextricably linked to our understanding of plate tectonics. Most volcanoes are found along plate boundaries, where the Earth's crust is being created or destroyed. At divergent boundaries, where plates are moving apart, magma rises to fill the gap, creating new crust. At convergent boundaries, where plates collide, one plate can subduct beneath the other, melting as it descends into the mantle and generating magma. The subduction process is a major driver of volcanic activity, leading to the formation of explosive volcanoes like those found in the Cascade Range or the Andes Mountains. The immense pressure and temperature variations within the Earth's crust play a fundamental role in these processes. Volcanic eruptions don't just represent immediate destruction. They also have long-term effects on the environment. The deposition of volcanic ash and lava can create fertile soils, supporting plant growth, and eventually contributing to the formation of new ecosystems. Over millions of years, volcanic activity has played a crucial role in shaping landscapes, creating iconic features like shield volcanoes, stratovolcanoes, and calderas. The geological record is replete with evidence of volcanic impacts, from the vast lava plains of Hawaii to the towering peaks of the Alps. The study of past volcanic events provides valuable insights into the behavior of present-day volcanoes and helps us to better understand the dynamic forces that shape our planet. It is a constant reminder that we inhabit a world of incredible power, a world where geological processes continue to sculpt the land and challenge our understanding of the Earth's incredible, ongoing transformation. Let's turn our attention now to a truly remarkable and often intimidating force of nature, volcanoes. These geological formations, born from immense heat and pressure deep within the Earth, represent a powerful demonstration of our planet's internal dynamism. They're not simply mountains, they're windows into the very processes shaping our world. As we explore their behavior, we'll uncover the intricate mechanisms behind their eruptions, revealing a science both dramatic and profoundly ancient. The immense heat driving volcanic activity originates from the Earth's core, a region of molten rock known as the mantle. This heat isn't just residual from the planet's formation, it's generated by radioactive decay within the mantle itself. Over millions of years, this heat causes the mantle rock to slowly melt and rise towards the surface. This molten rock, called magma, accumulates in underground reservoirs. The pressure within these reservoirs builds, creating a state of equilibrium, a balance between the forces pushing the magma upwards and the forces resisting its movement. The composition of this magma is key to understanding a volcano's eruption style. Magma isn't just molten rock. It's a complex mixture of dissolved gases, solid minerals, and crystals. These gases are particularly important because they dramatically influence the behavior of a volcano. The primary gases released during an eruption are sulfur dioxide, carbon dioxide, and water vapor. Sulfur dioxide is responsible for the characteristic pungent smell often associated with volcanic areas. It's a significant contributor to air pollution during eruptions, and its presence can have a substantial impact on surrounding ecosystems. Carbon dioxide, while present in smaller quantities, is a greenhouse gas and also poses a potential hazard if released in large amounts, displacing oxygen and creating pockets of unbreathable air. Water vapor, though seemingly innocuous, plays a vital role. It significantly increases the weight of the magma, contributing to the explosive nature of many eruptions. The amount of water vapor present directly correlates with the potential for a violent release. As we consider the conditions within these magma reservoirs, we realize that they are rarely, if ever, perfectly stable. Small changes in pressure, temperature fluctuations, or the introduction of new magma can disrupt this equilibrium. These disruptions trigger a process known as decompression melting. Essentially, the reduction in pressure allows more volatile gases to escape from the magma. This, in turn, lowers the melting point of the surrounding rock, initiating a chain reaction that can lead to a full-blown eruption. The type of magma, its viscosity, its gas content, and its chemical composition dictates the style of eruption. Highly viscous magma, meaning it's thick and sticky, tends to trap gases, leading to build-up of immense pressure and, consequently, more explosive eruptions. Conversely, less viscous magma allows gases to escape more readily, resulting in quieter, effusive eruptions characterized by the flow of lava. Now, let's examine how volcanoes vent this accumulated pressure. The process of venting is fundamentally about releasing the immense forces trapped within. Initially, this venting occurs through the release of gases. As magma rises towards the surface, the pressure decreases, and the dissolved gases begin to expand, forming bubbles. These bubbles, when they reach the surface, violently rupture, propelling a significant portion of the magma upwards in the form of a pyroclastic flow or an ash plume. Pyroclastic flows are incredibly dangerous, hot currents of gas and volcanic debris that race down the slopes of a volcano at hundreds of kilometers per hour. Ash plumes, on the other hand, can travel far beyond the immediate vicinity of the volcano, disrupting air travel and causing widespread ashfall. The scale of an eruption, its intensity and duration, directly correlates with the volume and speed with which these gases and debris are expelled. Beyond gas release, volcanoes also vent pressure through lava flows. These flows are the solidified remnants of magma that have made it to the surface. The movement of lava itself is a crucial component of the venting process. As magma ascends, it pushes aside the surrounding rock, creating pathways for further eruption. The shape and flow characteristics of these lava flows are influenced by several factors, including the viscosity of the magma, the slope of the terrain, and the amount of gas present. Some lava flows are relatively slow-moving and viscous, creating broad, gently sloping flows. Others are more fluid and fast-moving, forming channels and lava tubes. The resulting landscape, a testament to the power of volcanic activity, can be incredibly diverse, ranging from vast shield volcanoes to steep, conical stratovolcanoes. The relationship between magma movement and lava flows isn't always a simple one. During an eruption, the magma may not always flow continuously. Instead, there may be periods of intense eruption, followed by periods of relative quiescence. These periods of quiescence allow the magma to cool and solidify, creating new lava domes or plugging existing vents. This process of blockage and release can further contribute to the complex and dynamic behavior of a volcano. Furthermore, the shape of a volcano itself is heavily influenced by the type of eruptions it has experienced over time. Stratovolcanoes, for instance, are built up over centuries through alternating layers of lava flows, pyroclastic deposits, and ash. These volcanoes, also known as composite volcanoes, are often characterized by their steep slopes and symmetrical cones. Shield volcanoes, in contrast, are built from fluid basaltic lava flows, resulting in broad, gently sloping shapes. The study of volcanoes provides invaluable insights into the processes shaping our planet. Volcanic activity isn't just a destructive force, it's also a vital agent of geological change, contributing to the formation of new land, the recycling of materials within the Earth, and the release of gases that influence our atmosphere. The ongoing monitoring of volcanoes through seismographs, gas sensors, and satellite imagery is crucial for predicting eruptions and mitigating their potential impact. Understanding the complex interplay of factors that drive volcanic behavior is a testament to the profound power and enduring mystery of our planet. As we continue to explore and learn from these magnificent and occasionally terrifying geological formations, we gain a deeper appreciation for the dynamic nature of Earth. The Earth beneath us, a restless and powerful force, constantly reshaping our world through processes we often only glimpse in documentaries or read about in history books. Today, we're turning our attention to the spectacular and, at times, terrifying displays of nature, volcanoes. These are not simply mountains, they are expressions of the planet's internal heat, a visible reminder of the immense geological forces at play. We'll be examining some of the most significant volcanic events and their profound impact on the civilizations and landscapes around the globe. Let's begin by considering the sheer scale of these events. Volcanic eruptions can range from gentle effusions of lava to cataclysmic explosions that alter entire ecosystems and redraw coastlines. Understanding the intensity of these events is crucial, and that's where the Volcanic Explosivity Index, or VEI, comes into play. The VEI is a logarithmic scale, ranging from 0 to 8, used to quantify the magnitude of volcanic eruptions. A VEI of 0 indicates a very minor eruption, perhaps a small steam explosion. As the number increases, so does the potential for devastation. A VEI of 8, for example, represents a super-colossal eruption, the largest known volcanic events in Earth's history, capable of injecting ash and gas into the stratosphere, impacting global climate patterns for years to come. Scientists use a variety of data, lava flow volume, ash plume height, gas emissions to assign a VEI, providing a standardized measure of volcanic power. It's a fascinating system, allowing us to compare eruptions across different eras and locations, and to assess the potential hazards associated with any given volcano. Now, let's move forward in time and across continents to examine one of the most well-documented and tragically poignant volcanic events in human history, the eruption of Mount Vesuvius in 79 AD. Located in the Bay of Naples, Italy, Vesuvius had remained dormant for centuries, a seemingly tranquil giant looming over the bustling Roman Empire. It was a mountain considered sacred, even feared, but largely ignored in terms of any serious scientific observation. The local population relied on ancient myths and legends, attributing its power to the god Vulcan, the Roman counterpart to Hephaestus. However, beneath the surface, quietly beneath the fertile plains of Campania, magma was accumulating, building pressure. Around midday on August 24, 79 AD, the volcano erupted with astonishing force. Initially, the eruption was characterized by a Plinian phase, a towering column of ash, pumice, and gas shot high into the atmosphere, reaching altitudes of over 30 kilometers. Pyroclastic flows, superheated avalanches of gas and volcanic debris, raced down the slopes, incinerating everything in their path. The initial phase of the eruption was focused on the western side of the mountain, but the instability quickly spread, causing massive landslides and further triggering destructive flows. The immediate impact was devastating for the settlements nestled in the shadow of the volcano. Pompeii, a thriving Roman city renowned for its commerce and public baths, was buried under meters of ash and pumice. The speed of the burial, combined with the intense heat, meant that many residents perished instantly, either from the falling debris or from the suffocating effects of the ash. Herculaneum, a smaller town located closer to the volcano, suffered an even more complete destruction. The pyroclastic flows, moving at incredible speeds, overwhelmed the town, burying buildings and bodies alike in a thick layer of ash and volcanic material. The intense heat vaporized much of the organic material, creating a remarkable, albeit tragic, fossil record. The eruption continued for several days, eventually transitioning into a phase characterized by the emission of lapilli, small, pebble-sized fragments of volcanic rock and ash. As the main Plinian phase subsided, the mountain produced a vast, diffuse deposit of volcanic ash that stretched for hundreds of kilometers, blanketing surrounding areas and disrupting trade routes. It's estimated that tens of thousands of people perished in the immediate vicinity of the volcano, marking one of the deadliest volcanic events in recorded history. The city of Pompeii, remarkably preserved by the volcanic ash, offers an unparalleled window into the daily life of a Roman city, frozen in time by the fury of Vesuvius. Excavations began in the 18th century and continue to this day, revealing remarkably intact buildings, artifacts, and even the casts of the victims, a poignant reminder of the human cost of this catastrophic event. Beyond the immediate devastation, the eruption had significant long-term consequences. The volcanic ash altered the landscape of the Bay of Naples, burying agricultural lands and reshaping the coastline. The deposition of ash also affected water sources, impacting the local economy and population. The eruption of Vesuvius serves as a potent reminder of the awesome power of nature and the vulnerability of human settlements to volcanic hazards. Let's consider, for a moment, the sheer scale of the geological processes involved. Volcanoes are formed through a process of plate tectonics, the movement of Earth's crustal plates. At divergent plate boundaries, such as the mid-Atlantic ridge, magma rises to fill the gaps created by the separating plates. At convergent plate boundaries, where plates collide, one plate can subduct, slide, beneath the other, generating tremendous heat and pressure that melts the surrounding rock, creating magma. This magma then rises to the surface, erupting as volcanoes. The eruption of Mount Vesuvius, and indeed, virtually all volcanoes, is a testament to this fundamental geological process. As we continue to explore the world's volcanoes, we encounter a stunning array of types: shield volcanoes, composite volcanoes, also known as stratovolcanoes, cinder cones, and calderas. Each type is characterized by its shape, composition, and eruptive style. Shield volcanoes, for instance, are broad, gently sloping volcanoes formed by the accumulation of basaltic lava flows. Composite volcanoes, such as Mount Vesuvius, are characterized by their steep, conical shapes, formed by alternating layers of lava and pyroclastic material. Cinder cones are small, steep cones formed by the accumulation of ejected volcanic debris. Calderas are large, bowl-shaped depressions formed by the collapse of a volcano after a massive eruption. The study of volcanoes is not only scientifically fascinating, but also vitally important. Monitoring volcanoes, understanding their eruptive behavior, and developing effective hazard mitigation strategies are crucial for protecting communities living near these potentially dangerous natural features. The insights gained from studying volcanoes like Vesuvius can help us predict future eruptions, assess the risks, and ultimately save lives. The legacy of Mount Vesuvius, and indeed all volcanic eruptions, is one of both destruction and preservation. The ash that buried Pompeii has, ironically, preserved a remarkable snapshot of Roman life, offering invaluable insights into the past. The study of these events continues to shape our understanding of the Earth's dynamic processes and to inform our efforts to manage volcanic hazards. As we move forward, let's remember the lessons learned from Vesuvius and appreciate the powerful forces that continue to shape our planet. Let's turn our attention to the truly immense, forces residing beneath the surface of our planet, volcanoes. These are not simply mountains, they are expressions of a restless energy, a constant, slow, moving conversation between the Earth's interior and its outer shell. Understanding volcanoes offers a profound insight into the geological processes that have shaped and continue to shape our world. We'll explore events that demonstrate the raw power and the surprising sensitivity of these natural phenomena. Consider, for instance, the history of volcanic activity. The Earth's crust isn't a single, unbroken piece. It's divided into several large plates, constantly moving, albeit incredibly slowly, driven by forces deep within the planet. Where these plates interact, converge, diverge, or slide past one another, volcanic activity is most frequently observed. The immense pressure and heat generated within the Earth's mantle can melt rock, creating magma, which is less dense than the surrounding solid rock. This buoyant magma rises, seeking pathways to the surface, often along zones of weakness in the crust. The formation of mountain ranges, like the Andes or the Cascade Range in North America, is inextricably linked to this ongoing volcanic process. A particularly dramatic illustration of this process occurred on May 18, 1980, with the catastrophic eruption of Mount St. Helens in Washington state. Prior to the 1980 event, Mount St. Helens had been a dormant volcano for 86 years, having been dramatically altered by a landslide in 1968. This landslide removed a significant portion of the north flank, destabilizing the volcano and creating a large crater. The volcano was monitoring, of course, with scientists keenly aware of the changes, and a pre-existing bulge indicated a build-up of pressure. The eruption began with a series of low-frequency blasts, followed by a lateral blast, a massive surge of hot gas and ash that traveled across the surrounding landscape at speeds exceeding 700 kilometers per hour. The lateral blast was devastating, leveling forests and obliterating everything in its path. The eruption itself was a complex sequence of events, starting with a vertical explosion as the pressurized magma chamber collapsed. This collapse triggered a pyroclastic flow, a fast, moving current of hot gas and volcanic debris, which raced down the volcano's slopes. The eruption released an estimated 2.5 billion tons of material, dramatically reshaping the landscape and causing widespread devastation. The meticulous monitoring undertaken by the USGS, the United States Geological Survey, and the scientific community demonstrated the crucial role of data collection and analysis in predicting and mitigating the risks posed by volcanic activity. It served as a vital lesson in understanding the dynamic nature of volcanoes. Now, let's move our focus to a vastly different, yet equally significant, volcanic event, the 1883 eruption of Krakatoa. This eruption, occurring in the Dutch East Indies, modern-day Indonesia, remains one of the most powerful and globally influential volcanic events in recorded history. Krakatoa, then comprised of two volcanic islands, was already a known, though intermittently active, volcano. However, the events of August 26 and 27, 1883, were unlike anything previously witnessed. The initial explosions were colossal, generating a massive atmospheric pressure wave. Then, the caldera, the collapsed volcanic crater, collapsed entirely, plunging the islands beneath the waves. The sound of the eruption was heard thousands of kilometers away. The atmospheric pressure wave traveled around the globe, causing noticeable changes in air pressure and even altering the pitch of musical notes. This phenomenon, often described as the sound of silence, was due to the interference of the shock wave with sound waves in the atmosphere. The eruption produced an estimated 180 megatons of TNT equivalent, making it roughly 100 times more powerful than the eruption of Mount St. Helens. The energy released caused a significant increase in atmospheric temperature, triggering a global atmospheric event known as the Volcanic Year of 1883. This year was characterized by unusually bright sunsets and sunrises, caused by the scattering of sunlight by sulfate aerosols, tiny particles of sulfuric acid, ejected high into the stratosphere by the eruption. These aerosols persisted in the upper atmosphere for several years, reflecting sunlight and contributing to a noticeable cooling effect on the planet's surface. Furthermore, the eruption generated a massive tsunami, devastating coastal communities in Indonesia and beyond. The tsunami waves, generated by the underwater explosions, reached heights of over 40 meters in some areas, causing widespread destruction and loss of life. As we consider the contrasting nature of these events, the relatively contained devastation of Mount St. Helens, a more immediate consequence of a destabilized volcano, versus the widespread, long-term global reverberations of Krakatoa, we see a crucial point. Volcanic eruptions aren't just localized disasters. They are interconnected components of a complex planetary system. The gases released during an eruption, primarily water vapor and carbon dioxide, play a vital role in regulating Earth's climate. The sulfate aerosols, created by sulfur dioxide emissions, impact global weather patterns. The very shape of the landscape, the formation of new landmasses through volcanic activity, influences coastal environments and ocean currents. The study of volcanoes, therefore, extends far beyond simply predicting eruptions. It's about understanding the fundamental processes that govern our planet's environment and its long-term stability. It's about recognizing the power lurking beneath our feet and appreciating the delicate balance between geological forces and the conditions that support life as we know it. The continued monitoring and research into these dynamic systems is essential, not only for protecting communities vulnerable to volcanic hazards, but also for gaining a deeper understanding of the planet we inhabit. The legacy of Mount St. Helens and Krakatoa reminds us that the Earth is a place of constant transformation, a place where immense forces are perpetually at play. Let's turn our attention today to a force of nature, unlike almost any other volcanoes. These geological giants represent a raw, primal energy, a constant reminder of the dynamic processes shaping our planet. Their power is both terrifying and captivating, a spectacle of heat and destruction interwoven with the potential for renewal and the creation of new landscapes. We'll explore some particularly significant examples, focusing on their behavior and the science behind their incredible activity. Consider, for a moment, the sheer scale of a volcanic eruption. The forces involved are immense, driven by the movement of molten rock, magma, beneath the Earth's surface. This magma is formed deep within the crust, often where tectonic plates collide or diverge, creating pathways for the molten rock to ascend. The temperature at these depths can reach extraordinary levels, and the pressure building up is truly astounding. When this pressure becomes too great, a release occurs, an eruption. The nature of that eruption can vary dramatically, ranging from gentle flows of lava to explosive events that send ash and rock soaring into the atmosphere for hundreds, even thousands of kilometers. Let's begin with a location that exemplifies consistent, dramatic activity, Mount Etna, situated on the island of Sicily in Italy. It's a truly remarkable example of a perpetually active volcano. Mount Etna has been erupting for at least 250,000 years, and its activity has profoundly shaped the surrounding landscape, influencing the lives of the people who have called this area home for millennia. The volcano's activity is intimately linked to the African plate subducting beneath the Eurasian plate. This ongoing process creates a zone of intense geological stress, fueling the magma chamber beneath Etna. It's one of the most frequently active volcanoes on the planet. Unlike some volcanoes that exhibit long periods of dormancy, Etna frequently experiences strombolian eruptions, characterized by bursts of gas and lava that build up and collapse, generating spectacular fountains of ash and incandescent rock. The volcano's cone has grown steadily over time through successive eruptions, a visible record of its continuous activity. The fertile volcanic soils produced by Etna's eruptions contribute significantly to the region's agricultural production, a testament to the inherent dynamism of the landscape. Monitoring of Etna is incredibly sophisticated, utilizing seismographs, gas sensors, and satellite imagery to track changes in the volcano's behavior and provide early warnings to local populations. Now, let's shift our focus to a location that represents a profoundly different kind of volcanic threat: Yellowstone National Park in the United States. Yellowstone is dominated by the world's largest active geyser, Old Faithful, but its significance extends far beyond that famous eruption. Yellowstone is actually a gigantic caldera, the remains of a massive supervolcano. This isn't just a single, isolated volcano, it's a complex system of interconnected magma chambers and hydrothermal features. Approximately 1.3 million years ago, Yellowstone experienced one of the largest volcanic eruptions in recorded history. This eruption ejected an estimated 1,000 cubic kilometers of material ash, rock, and gas across a vast area. The force of the eruption reshaped the landscape dramatically, creating the enormous caldera that now defines the park. What makes Yellowstone so significant is the potential for another supereruption. Beneath the park lies a magma chamber, estimated to be hundreds of kilometers in diameter, filled with molten rock at incredibly high temperatures. The tectonic setting, the Pacific Plate subducting beneath the North American Plate, continues to provide the energy necessary to fuel the system, while a full-scale supereruption is considered a low-probability event, occurring on timescales of hundreds of thousands of years. The potential consequences are truly staggering. An eruption of this magnitude would have global repercussions, causing widespread ashfall, disrupting climate patterns, and potentially triggering devastating environmental effects. The ground deformation, the swelling and shrinking of the Earth's surface in Yellowstone, is a key indicator of the magma chamber's activity. Scientists carefully monitor ground movement using GPS stations and satellite radar. Small, frequent earthquakes are common in the region, reflecting the constant movement of magma beneath the surface. The hydrothermal features, geysers, hot springs, and mud pots are a direct result of the intense heat from the magma chamber interacting with groundwater. These features demonstrate the incredible heat flowing beneath the surface and provide valuable insights into the volcanic system. It's important to understand that the term supervolcano often evokes a sense of immediate danger. However, volcanic systems like Yellowstone are inherently complex and can exhibit a wide range of behaviors. The current level of activity isn't necessarily indicative of an imminent eruption. Instead, it's a reflection of the ongoing geological processes that have shaped this region for millennia. Scientists continue to study Yellowstone, not to predict a specific event, but to improve our understanding of volcanic systems and develop strategies for mitigating risk. Moving beyond these two distinct examples, we can consider other significant volcanic areas around the globe. The Pacific Ring of Fire, encircling the Pacific Ocean, is home to the majority of the world's active volcanoes. This region is characterized by intense tectonic activity, where plates are constantly colliding, separating, and sliding past each other. The Andes Mountains in South America, the Cascade Range in North America, and the volcanic islands of Japan and Indonesia all represent areas of intense volcanic activity. Each volcanic system has its own unique characteristics and hazards, shaped by its specific tectonic setting and geological history. Ultimately, volcanoes represent a fundamental force of nature, a reminder of the dynamic processes that have shaped our planet and continue to do so today. Studying these geological giants provides invaluable insights into Earth's history, the processes that drive plate tectonics, and the potential hazards we face. The sheer scale of these events, coupled with the ongoing monitoring and research efforts, underscore the importance of understanding and respecting the power of the Earth beneath our feet. As we continue to explore and learn, we gain a deeper appreciation for the interconnectedness of our planet and the ever-changing nature of its landscapes. Let's turn our attention today to a force of nature, both breathtaking in its scale and profoundly ancient in its origins: volcanoes. They represent a primal energy, a reminder of the constant, transformative processes shaping our planet. We'll be exploring a selection of these geological wonders, examining their formation, their behavior, and the deep connections they've forged with human cultures over the millennia. Let's begin with a journey to Japan and the iconic Mount Fuji. This majestic stratovolcano, often simply called Fuji-san by the Japanese, isn't just a beautiful sight. It's a repository of history and spirituality. Its formation began approximately 3 million years ago, a gradual accumulation of volcanic rock and ash triggered by the subduction of the Pacific Plate beneath the Eurasian Plate. The movement of these plates creates immense pressure and heat deep within the Earth's crust, eventually leading to the melting of rock and the subsequent eruption of molten material, magma, which rises to the surface. The initial eruptions of Mount Fuji were likely quite different from the cone we see today, characterized by more explosive and violent activity. Over time, the lava flows solidified, building up the layers that constitute the volcano's distinctive shape. The last significant eruption occurred in 1707, a truly colossal event known as the Honshu earthquake Fuji eruption, a devastating combination of seismic activity and volcanic explosions that reshaped the surrounding landscape. The sacred status of Mount Fuji is deeply rooted in Japanese Shinto and Buddhist beliefs. It's revered as a dwelling place for the goddess Konohana, Susa, the deity of agriculture and fertility. Throughout history, it has been considered a symbol of beauty, strength, and spiritual purity. Emperors have traditionally ascended the mountain for purification ceremonies, and pilgrims have journeyed to its slopes seeking enlightenment. The mountain's symmetrical shape, a result of its consistent eruptions and volcanic flows, has further enhanced its symbolic importance, representing harmony and balance. The act of climbing Fuji-san is still a significant cultural event for many Japanese people, a pilgrimage of both physical and spiritual endurance. Even today, numerous visitors undertake the challenging climb, particularly during the short window of time each year when the mountain is officially open for ascent, a period deeply intertwined with Japanese tradition and national identity. Now, let's shift our focus to the Pacific Ocean and the dynamic island chain of Hawaii. Here, we encounter Mauna Loa, the world's largest active volcano, measured not just by its base, but also by its height when measured from its underwater base to its summit. Mauna Loa's story is one of immense geological time, beginning approximately 800,000 years ago, though evidence suggests volcanic activity in the area stretches back even further. Unlike the layered structure of Mount Fuji, built through successive eruptions, Mauna Loa's formation is characterized by relatively fluid, basaltic lava flows. These flows are incredibly rich in magnesium and iron, giving the lava its distinctive dark gray color. The volcano's activity is directly linked to the Hawaiian Emperor Seamount chain, a linear series of volcanoes formed by the continuous movement of the Pacific Plate across a hot spot, a plume of magma rising from deep within the Earth's mantle. The shield shape of Mauna Loa is a direct consequence of this style of eruption. Because the lava is relatively fluid, it spreads out over vast distances, creating gently sloping, shield-like formations. The volcano's caldera, a large, bowl-shaped depression at its summit, is formed by the collapse of the summit area after massive eruptions. The volcano's activity isn't always gentle, It's known for its powerful, sustained eruptions, capable of producing significant lava flows that can cover vast areas. The 1984 eruption of Mauna Loa was one of the most significant in modern times, producing a large lava flow that traveled down the volcano's flanks and eventually reached the coastline, dramatically reshaping the landscape. Monitoring of Mauna Loa is incredibly important, utilizing sophisticated seismographs and GPS technology to detect changes in ground deformation, which can provide early warning signs of an impending eruption. The Hawaiian Volcano Observatory, a division of the United States Geological Survey, plays a crucial role in tracking and predicting volcanic activity, protecting the communities living near the volcano and contributing to our understanding of these powerful natural forces. As we consider the differences between Mount Fuji and Mauna Loa, a key distinction emerges: the scale of their formation and the types of eruptions they produce. Mount Fuji represents a relatively localized, layered volcanic process shaped by the compression of tectonic plates. Mauna Loa, on the other hand, is a product of a broader, more continuous geological process driven by the movement of a mantle hotspot. Both volcanoes share a common foundation: the incredible heat and pressure within the Earth, but they manifest in vastly different ways. The consistent flow of magma, the subtle shifts in plate movement, and the varying chemical composition of the lava are all factors that contribute to the distinct characteristics of each volcanic wonder. Looking at volcanoes globally, we see a stunning array of forms and behaviors. Some are characterized by explosive eruptions, sending ash and gas high into the atmosphere. Others are known for their slow, effusive eruptions, creating vast lava plains. The color of the lava itself, from the dark gray of Mauna Loa to the paler shades seen in some other volcanic areas, depends on the composition of the magma. The study of volcanoes isn't just about predicting eruptions. It's about understanding the very processes that shape our planet. Volcanoes provide invaluable insights into plate tectonics, mantle dynamics, and the evolution of the Earth's crust. They are, in essence, laboratories of geological time, offering us a tangible connection to the forces that have sculpted our world for billions of years. Their continued activity serves as a constant reminder of the dynamism inherent within the Earth. Over millions of years, the Earth's crust has been shaped by immense forces, and among the most dramatic displays of this power are volcanoes. These geological behemoths, born of molten rock and subterranean heat, represent both terrifying destruction and the very creation of new land. We're going to explore some of the world's most fascinating volcanoes, examining their unique characteristics, ongoing activity, and the scientific efforts dedicated to understanding these powerful natural phenomena. Let's begin with Vilarica, nestled in the heart of Chile. This impressive stratovolcano is a textbook example of a conical mountain formed by the repeated accumulation of lava flows and volcanic debris. Its steep slopes, a result of the explosive layering of materials, rise dramatically from the surrounding Patagonian landscape. Vilarica remains highly active, frequently exhibiting steam and gas emissions, a constant reminder of the molten fury simmering beneath the surface. Researchers actively monitor the volcano, utilizing seismic data and gas measurements to predict potential future eruptions. Moving eastward, we encounter Sakurajima, a perpetually active volcano situated near Kagoshima in Japan. Unlike Vilarica's relatively contained eruptions, Sakurajima presents a more consistent threat. It's a composite volcano, continually rebuilding itself through lava flows and pyroclastic deposits. The frequent activity, often involving ash plumes reaching considerable heights, has a significant impact on the lives of the surrounding population, necessitating sophisticated early warning systems and evacuation plans. Studying Sakurajima offers invaluable insight into the dynamics of subduction zone volcanoes, where one tectonic plate slides beneath another. Now, let's journey to Africa, specifically to Mount Kilimanjaro in Tanzania. This iconic mountain is a dormant stratovolcano, yet its history is inextricably linked to ice. For a significant portion of the last few millennia, Kilimanjaro was capped with a substantial glacier. However, due to rising global temperatures, the glacier has dramatically retreated, a stark visual demonstration of climate change's impact. Scientists continue to study Kilimanjaro, analyzing the remaining ice, glacial meltwater, and surrounding landscapes to understand the complex interplay between volcanic activity and glacial processes. The volcano itself is still active, occasionally displaying fumarolic activity, and its future evolution will be heavily influenced by ongoing warming trends. Venturing into the Indian Ocean, we find Piton de la Fournaise on the island of Réunion. This active shield volcano is a prime example of a volcano built from fluid, basaltic lava. Its eruptions are typically characterized by relatively gentle lava flows that spread across the volcanic flanks, creating vast shield-shaped formations. Piton de la Fournaise is renowned for its long periods of quiescence, punctuated by occasional, predictable eruptions, offering researchers a unique opportunity to study the evolution of a shield volcano over extended periods. Shifting our focus to the Americas, we arrive at Nevado Ojos del Salado, located on the Argentina-Chile border. This remarkable volcano holds the title of the highest active volcano in the world, standing at an astounding 893 meters above sea level. Its location within the Andes Mountains, a zone of intense tectonic activity, contributes to its persistent activity. Ojos del Salado's eruptions are often characterized by the release of steam and gas and occasional explosive events, fueled by the high altitude and volatile gases trapped within the magma. Moving south, we encounter Popocatépetl, a frequently active stratovolcano situated close to Mexico City. This volcano poses a significant hazard to the densely populated metropolitan area, and its activity is closely monitored by a network of seismographs and gas sensors. Popocatépetl eruptions can range from small steam emissions to powerful explosive events, and the potential for ashfall impacting the surrounding region is a constant concern. Eastward again, we reach Kamchatka Volcanic Arc in Russia. This region is a truly remarkable example of a highly volcanic area, formed by the subduction of the Pacific Plate beneath the North American Plate. The arc is characterized by numerous active and dormant volcanoes, including Klyuchevskaya Sopka, one of the world's most active volcanoes. The region's complex geological setting contributes to its intense volcanic activity, producing frequent eruptions and the formation of new volcanic land. Now, let's delve beneath the ocean's surface to explore Emperor Seamount's underwater volcanoes. These submerged volcanoes, formed by the same processes driving volcanic activity on land, play a crucial role in shaping the ocean floor. They create unique habitats for marine life and contribute to hydrothermal vent systems, where specialized ecosystems thrive around the hot, mineral-rich waters. Exploration of these underwater volcanoes is a challenging but rewarding endeavor, providing valuable insights into the geological processes occurring beneath the waves. Further exploration brings us to the Longfin Caldera in Wyoming. This submerged volcanic caldera, a remnant of a massive eruption millions of years ago, now lies beneath the floor of the Atlantic Ocean. Scientists are actively studying Longfin Caldera, analyzing its geological features and the surrounding marine sediments to reconstruct the eruption's history and understand its impact on the region. Moving to Iceland, we find Hekla, one of the most active volcanoes in Europe. Its frequent eruptions, often characterized by explosive lava flows, have profoundly shaped the Icelandic landscape. Studying Hekla provides vital information about the subglacial volcanic processes operating within Iceland. Consider Mount Etna in Sicily, Italy, Its persistent activity adds to the challenging nature of studying volcanic systems in a densely populated region. The frequent ashfall from eruptions has impacted agriculture and air travel, highlighting the complex interactions between volcanoes and human societies. Continuing our global survey, we examined the Tana volcano in Vanuatu, where the indigenous population relies on the volcano's thermal waters for heating and spiritual practices, a remarkable example of human-volcano interaction. The volcanic system of Stromboli, an island in the Aeolian archipelago north of Sicily, is renowned for its persistent, low-level activity, producing spectacular displays of submarine explosions, a constant reminder of the power held within. We might also note the ongoing research focused on the Reykjanes Ridge in Iceland, a mid-ocean ridge where new crust is constantly being formed and where volcanic activity is intricately linked to plate tectonics. The volcanoes of the Azores Islands in the Atlantic Ocean demonstrate the power of hotspot volcanism, where a mantle plume generates heat that rises to the surface, creating chains of volcanic islands. The volcanic area of Molossus on the Crimean Peninsula represents an area of intense geological interest, exhibiting evidence of complex tectonic activity and multiple volcanic episodes. Looking towards New Zealand, we can examine the diverse volcanic landscape of the Taupo volcanic zone, which includes Mount Ruaipu and Mount Tongariro, active volcanoes within a geothermally active region. In the Philippines, Mount Mayon's perfectly conical shape is a testament to the power of stratovolcanic processes, presenting a unique challenge for scientists attempting to understand its dynamics. The volcanic activity within the Cascade Range of North America, encompassing Mount St. Helens and Mount Rainier, represents a critical area for studying the processes of landslides, pyroclastic flows, and debris flow hazards. The Galapagos Islands, formed by hotspot volcanism, provide an exceptional laboratory for studying evolutionary processes and the formation of new landmasses. The volcanic areas of Papua New Guinea showcase a diverse range of volcanic features, including stratovolcanoes, shield volcanoes, and caldera complexes. The volcanic systems of the Canary Islands, influenced by the mid-Atlantic ridge, provide valuable insights into the formation of oceanic islands and the impact of volcanic activity on climate. The scientific exploration of the volcanic region of the Afar Depression in Ethiopia, a UNESCO World Heritage Site, focuses on the study of hydrothermal systems and the origin of life. The volcanic areas of Iceland continue to be a focus of intensive research, with scientists studying the interactions between magma, ice, and groundwater. The ongoing monitoring of volcanoes in the Andes Mountains of South America contributes to our understanding of plate tectonics and volcanic hazards. The volcanic activity in the South Pacific region, including the islands of Samoa and Tonga, presents a unique opportunity to study the effects of underwater eruptions on marine ecosystems. The research efforts focused on the Yellowstone National Park volcanic system in the United States aim to understand the dynamics of a supervolcano and assess the potential hazards it poses. The geological survey of the Vatnajökull ice cap in Iceland combines studies of volcanic activity with investigations of glacial processes. The exploration of the volcanic areas of the Azores Islands continues to provide valuable insights into the formation of oceanic islands and the impact of volcanic activity on climate. The ongoing monitoring of volcanoes in the Pacific Ring of Fire, a region characterized by intense seismic and volcanic activity, is crucial for mitigating potential hazards. The study of the volcanic processes associated with seafloor spreading zones, such as the mid-Atlantic ridge, contributes to our understanding of plate tectonics and global climate change. The exploration of the volcanic regions of Indonesia, a country with a high density of active volcanoes, focuses on understanding the risks posed to local communities and developing effective mitigation strategies. The research into the dynamics of mantle plumes, upwellings of hot material from the Earth's interior, is helping scientists unravel the origins of volcanic activity around the world. And as our exploration of volcanoes comes to rest, let your thoughts drift, calm and unhurried, until sleep finds you. Good night.